There are two puzzles, two mysteries about our existence in this universe that have haunted me for years now. But finally, new Cool Worlds Lab research has presented an answer, a solution with massive ramifications for alien life. Less than 2.5% of all stars are G-dwarfs, whereas M-dwarf stars alone make up a staggering 82% of them. In other words, they are 33 times more common. An analogy here would be to wake up one day and somehow have totally forgotten where you were born, nor indeed you know nothing about your race or parentage. Now imagine someone put a gun to your head and asked you to guess which group of nations you originate from. Group 1, which contains the top 60 nations ranked by population, going all the way from India to Sri Lanka, or Group 2, which contains the next 12 nations spanning Malawi to Cambodia. That's the same percentage split as between M and G-type stars, and you would be 33 times more likely to survive this macabre experiment if you chose Group 1. But of course, the thing with statistics is that it's, well, statistical. 1 in 33 times, you will be wrong by making this choice. And so, yes, there are some of you watching this right now who were born in Group 2 and you are thinking to yourself, what's the problem? But the point is that the vast majority of you are not from Group 2. That's just statistics. In other words, in our guessing game, picking Group 2 means you are much more likely to be wrong. Now, if this was the only mystery, I think we could overlook it. A 33-to-1 oddity, it's not a huge deal, but it gets much worse because of Puzzle 2, which is intimately related. You see, M-dwarfs live far longer than G-type stars. We're talking 10 trillion years versus 10 billion years. So think about that. Trillions of years from now, a time far exceeding the current age of the universe, there will still be a colossal number of these M-type red dwarfs littered across the cosmos. Yet more, we know from recent exoplanet studies that these often have rocky planets in their habitable zones. In fact, probably even more so than G-type stars. So this all culminates in a second puzzle. Why do we live so early in the so-called stelliferous period of cosmic history, the period where stars exist? Indeed, we seem to live at the first 0.1% of this episode, a 1,000-to-1 peculiarity. Put both of these puzzles together, and something seems awfully suspicious about these M-dwarfs. It is highly surprising that we do not live around one. This realization is known as the red sky paradox, and we've talked about it on this channel before. You can watch our earlier video for that. Now, I have spent years thinking about these puzzles. It feels like a distant whisper from the universe, a subtle clue that most just pass by, but could actually be trying to tell us something, maybe something profound. Before I get into how to explain these puzzles, these videos take a lot of effort to produce, and that's why we are so grateful to our friends over at Incogni for supporting this video, a service dedicated to keeping you safe online. You know, when I was a kid, I remember using the internet during a time which some call the golden era of the internet. It was a period of anonymity. Nobody used their real names online because why would you? But these days, I feel like I have to enter my personal details several times a day, and it never feels right. The truth is that companies are scraping your data and selling it on without your permission, compromising your privacy in incalculable ways. Every time you do this, there's a chance that that data can end up in the hands of data brokers, and if it leaks or gets sold, criminals can use it for phishing, fraud, or to open credit accounts or worse. There's a narrative out there that this is just the way it is. That's just life. You just have to eat it. But look, it doesn't have to be this way. Incogni's team scour databases for your information, and when they find it, they bombard them with legal demands for its removal. In my case, I have personally benefited from over 1,400 successful data removals. And if you stumble across your info somewhere online and you're not happy about it, their new custom removals feature makes it easier than ever to get that taken care of too. For me and my family, Incogni has become an essential part of our safety online, and I encourage you to check this out. So to get started with an exclusive deal of 60% off their annual plan, head to incogni.com/coolworlds and use the code coolworlds. Once again, that's incogni.com/coolworlds and use the code coolworlds, link down below in the description. Now back to the video. Okay, so let's dive into explanations for our 2 existential puzzles. First off, it could just be luck, right? No need to invoke any physical explanation whatsoever, it was just sheer happenstance. Let's call that the luck hypothesis. Second, it could be that stars below some certain mass just don't develop observers like ourselves. We can speculate as to why or how that happens, and there are many good justifications, but all that really matters for now is that somehow the development of creatures like us is heavily suppressed around these stars. Let's call this the desolate M-dwarf hypothesis. A third and more subtle possibility is that planetary biospheres have finite lifetimes. Thus far, we have implicitly assumed that a planet could sustain life for trillions of years, but plausibly, plate tectonics would shut down before that, with potentially ruinous consequences for creatures like us. So we'll call this the truncated window hypothesis. So in my new paper, I throw the awesome power of Bayesian statistics at these 2 puzzles to figure out which explanation, if any, works. The 2 puzzles represent our data, or here our observations, features that require explanation by our model. And here, our model actually encompasses all 3 hypotheses. So we imagine that there is some critical mass below which stars are simply inhospitable. Let's call that the symbol M crit. And on top of that, there is also some temporal window for planetary life. Let's use the symbol T win. Subtly, the luck hypothesis is implicitly built into this because we can always evaluate this model at the extreme ends where both effects are negated. So in Bayesian parlance, our task is to figure out or infer this probability distribution, the probability of getting various values of M crit and T win given the data in hand, which here is our 2 puzzles. Essentially, we want to learn M crit and T win from the data. This function is known as the joint posterior. The whole Bayesian part comes in by application of Bayes' theorem, which lets you expand so-called conditional probabilities like this as follows. The first term on the right-hand side looks similar to before, but it flips the conditional around, so it represents the probability of getting the data given some choice of M crit and T win. That's known as the likelihood function. After that, we have the parameter priors, which are typically just assumed to be flat, uninformative distributions. And finally, down below, we have the so-called Bayesian evidence. We can calculate that as simply the integral of the numerator, but the important thing for us is that it formally represents the probability of getting the data. If we are being super rigorous here, then we should really say that it's the probability of getting the data given whatever model assumptions we made. So here, that's both the desolate M-dwarf scenario and the truncated window hypothesis are in effect. Remember this term because it's going to come out later when we want to compare models. The likelihood function is the real meat and potatoes of any good Bayesian analysis, and in this case, we're going to need an astrophysical model to evaluate it. An astrophysical model that's going to have to include several key laws. First, the rate at which stars are born is not the same at all times. In fact, the peak star formation rate occurred 10 billion years ago, and that's sometimes called cosmic noon. It's been gradually decreasing ever since. Eventually, no more stars will be born as the reservoirs of hydrogen are exhausted. The second law we need to know is how long do stars even live for? Massive stars live wild, short lives. They're kind of like the James Deans of the universe. But stars smaller than about 70% the mass of our sun live for so long that the universe isn't yet old enough for any of them to reach their final phases yet. Detailed astrophysical calculations by Fred Adams and Greg Laughlin estimate that the lowest mass stars should persist for a stunning 10 trillion years, and their result allows us to predict the lifetime of really any star we want. Finally, we need to know what fraction of stars are born as M-dwarfs versus K-dwarfs versus G-dwarfs, etc. This is known as the initial mass function, or IMF, and fortunately in astronomy it has been the subject of decades of study, and so we know this pretty damn well. Putting it all together, we can simulate 1 million stars over cosmic history as shown here. The x-axis is time since the Big Bang in billions of years on a log scale, so we would live here. And the y-axis is the number of suitable stars for observers like us over time. I say suitable because stars have a pretty hectic early life known as their pre-main sequence phase, and I decided to treat this period as basically being inhospitable. The final curve hopefully matches the intuition we have gained together. Early on, there are few stars because the star formation rate is low, but it peaks after a few billion years. By about 60 billion years, no more stars are made in our simulation, and so everything you see here is just long-lived stars. As we approach the 10 trillion year mark, even the smallest and longest lived stars sputter out. Now, this curve that we're looking at assumes that there is no mass cutoff or truncated window for planetary lifetimes. If we gradually increase the mass cutoff in small steps, we can see the curve shifts towards the left. As that cutoff gets closer to the mass of our sun, the current age of the universe looks less and less like an outlier and more like a typical observed sample, which of course is exactly what we want. You can make the same graph by truncating the habitable window instead, which ostensibly looks quite similar. However, a key issue with this model is that it only explains puzzle 2, why do we live so early in the universe? It has no ability to explain puzzle 1, why don't we live around an M-dwarf? So perhaps it's not surprising that when we compare these different models using the Bayesian evidence values that I mentioned earlier, the truncated window hypothesis doesn't fare too well. When we compare two models, we do so using the Bayes factor, which is the ratio of two evidences. So that means that the Bayes factor is the relative probability of getting the data given model A versus model B. So for example, we could compare the Bayes factor of getting the data given that there is some M-crit and T-win cutoff in action versus a model where they don't act at all. In other words, it's just the pure luck scenario. The Bayes factor comes out here at a whopping 1,600. That is huge. Usually, we would say that anything above 10 to 1 is classified as strong evidence, and anything above 100 to 1 is typically called decisive evidence. We literally don't have words to describe numbers which are higher than 100 to 1. So at 1,600 to 1, we really just don't have a leg to stand on by insisting that these puzzles are the outcome of random happenstance. Okay, so what about comparing the two hypotheses against one another directly? Well, as alluded to earlier, the truncated window hypothesis doesn't do great here, beaten out by the desolate M-dwarf scenario, and the reason why is because it has no ability to explain why our sun is a G and not an M. Whether you consider both explanations acting together or just the M-dwarf desolation scenario in isolation, you end up with a very similar cutoff that all stars below about half the mass of the sun are inhospitable. But throwing out truncated windows altogether is pretty questionable. After all, we have a strong physical basis to believe that planets should have finite lifetimes. They can't remain geologically active forever. We found that fixing that time to about 10 billion years causes this mass cutoff to reach the smallest possible value we can engineer, 0.34 solar masses to 95% confidence. That number sounds small, but it actually excludes 2/3 of all stars in the universe as developing observers like ourselves. 2/3. In support of this estimate, a 10 billion year planetary lifetime lines up nicely with predictions coming out of geophysics about the lifetime of plate tectonics on the Earth. To me, this is a pretty profound result, and it is interesting to ponder. Strictly speaking, this analysis only concerns the emergence of observers such as ourselves, in other words, intelligent life. But if 2/3 of all stars in the universe cannot produce observers, what does that say about the emergence of more simple life? Now, it is possible they indeed go ahead and form simple life, no problem, but then for some reason the properties of their star prohibit the evolution to complexity. But it's difficult to imagine what could possibly cause that, whereas we can certainly think of reasons why M-dwarfs could be inhospitable to life, full stop. For example, after their birth, M-dwarfs can take up to 1 billion years, or sometimes even more than that, to settle down into a normal star, and during that time, they are constantly hurling high-energy radiation at their planets, potentially stripping them of water and even an atmosphere. Indeed, initial studies of the rocky planets around the M-dwarf TRAPPIST-1 using the James Webb Space Telescope are yet to detect an atmosphere around any of the 7 planets, and it also strongly suggests that the inner 2 worlds at least are completely barren rocks. It's a strange situation. Using 2 ostensibly benign observations about ourselves, we've arrived at the sweeping conclusion that most of the universe is dead. I know, before you jump into that comment section that there are lies, damn lies, and statistics, but I think that we should take this seriously. The truth is that 1600 to 1 is just really steep odds to try and sweep under the rug as being the product of random happenstance. It is, for example, far above the canonical threshold used by scientists to discover, say, a new planet, or really a new anything. If we do not accept this level of odds as being a detection, then all sorts of modern discoveries are in deep trouble. Yet more, it naturally resolves not only the 2 puzzles at the core of this problem, but also James Webb's recent results and even the Fermi paradox itself. Now, since stars heavier than about 1.6 solar masses live too short to life for evolution to play out, when it comes to intelligent life in the universe, there could very well be a solar hegemony. I know many of you don't trust Bayesian statistics, so let's just zoom out for a second on this. All a Bayes factor really tells us is what the data supports. It's the probability of getting the data given some hypothesis. It is not the same thing as perhaps what you might really care about, the probability of the hypothesis given the data. To get that, you would have to invoke some prior for the hypothesis. The problem with this is that in general, we are all going to approach a problem with a different set of prior beliefs. So, for example, you might believe a priori that M dwarfs are great places for life, whereas a priori, I might be agnostic about it. And so when we go through this process of calculating odds ratios and comparing numbers, we are going to have different answers to one another. But the thing is that that is true in all of science with whatever question we ask. The only thing that we can all agree on is the Bayes factor. How well is the data explained by each hypothesis? I think the best way to think about this is that rigorously, the Bayes factor represents the factor by which your beliefs shift after seeing the data. So even if your prior belief is that M dwarfs are, say, 1 billion times more likely to be inhabited than G-type stars, the Bayes factor forces you to shift that belief by a factor of roughly 1,000 here. So now your belief would become 1,000,000 to 1. Your prior belief is up to you. I can't prescribe that. Nobody can. But despite that, we all have to agree that accounting for these 2 puzzles shifts our belief by a factor of 1,000. That is ironclad. This is very subtle, guys, but if you understood what I just said, then you already have a command of Bayesian statistics far in excess of most astronomers, trust me. Before wrapping up, let me add that I did consider a bonus hypothesis towards the end of the paper, but one which is much more radical in nature, that the universe itself becomes inhospitable to life at some future date. So to explain that, we could imagine something like a universe-ending false vacuum decay, or it could be groups of malevolent aliens or AIs gradually sterilizing the entire cosmos, and that's an idea actually known as grabby aliens, which we've spoken about on here before. But long story short, this explanation ends up being about 2 times worse than the truncated window hypothesis, which remember was already doing really poorly, so I don't give this much credence despite how cool it is from a sci-fi perspective. Okay, so final thoughts. I think that the solution presented, that low-mass stars do not develop observers, provides by far the best explanation as to our existence. But to truly prove such a claim would of course require testing, and fortunately, like all good scientific hypotheses, it is eminently falsifiable. If my claim holds true, then civilizations will not develop around low-mass stars. Now, they might still eventually get there though, perhaps by colonization or something, because that is a scenario for which we are not a representative sample, and thus we have no data either way. But barring interstellar colonization, M dwarfs should be very quiet places. That's my best bet. I think it is rigorously the most likely position based on the available data, but let me know what you think down below in the comments. Do you think that M dwarfs can develop intelligent life around them? And if not, what is special about our sun that prevents them around these M dwarf stars? These are the kinds of questions that awaken the soul and occupy a restless mind, and I hope that they spark some wonder in you. So until next time, stay thoughtful and stay curious. Thanks so much for watching, guys. I don't think you will find another YouTube channel that is doing quite what we are trying here on Cool Worlds. This is a research group, and this video was about a new research paper from our team, supported by many of you. In fact, I want to give a huge shout out to our two latest supporters, that is Steve Larter and Marison Adler. Thank you so much for your support. If you too want to become a Cool Worlder, you can use the link up above and down below, where you can support our research from as low as a cost of a coffee per month. So please do check that out.